Okay, so I hear that some presentations earlier. I feel like what I'm going to say has some connections to many of you said or something like this, but I want to do something. I don't know all of you, but I have got the feeling that, let's say half of you knows physics, quantum mechanics, and so on. Half of you is data scientists, machine learning, and half of you know both. Okay, so I would try to step back. And step back means what I mean by step back is I want to talk about quantum mechanics, the root of quantum mechanics. I'll step back, so it'll be for the physicists, it'll be just refreshing, and hopefully I'll use that to get somewhere. So how it works? Well, first to mention something, I'm from computer vision, as I see me. In computer vision, we do sometimes we formulate things as optimization. If I want to find a circle with some deformation, some noise, I may define the formula for the circle. I may do parameter estimation for the center and for the radius, some of the data that are shown to be Gaussian noise. And we estimate parameters, and sometimes we solve these problems with optimization. It's a common trending. I have to learn how to use this. And then other problems is, finding multiple ellipses, deformed circles. These circles, one overlapping over the other, they're deformed. Here, there's somehow in clutter. So those are basic optimization problems that appear in computer vision. uh, Extending to machine learning and to computer vision connections, the clustering. Many of you have seen many talks with this formula. And so this is trying to find clusters, the mixture of Gaussians, and you want to find the center of the Gaussians, the variance, the proportions, how many points. And the first algorithm is the EM. You choose to find all the parameters, and people find parameters. You give data, and you find parameters, and works as well as it does. And then, as a curiosity, there is also, this is more to my heart of curiosity, there are variational problems too. So the Elastica is one of the nice ones that appear in computer vision. The Elastica is to find curves that minimize the curvature all over and the length. And it's an old, beautiful problem. And in computer vision slash math, Mumford introduced the statistical framework for that. And it has an equation out of it, the equation for the density of the probability. And it has been studied, has been applied in computer vision, in painting, some problems, but it's a specific one. I just brought it up because it's a variational problem. On continuous is an interesting problem itself. I think there was a solution a few years ago uh, that seems to be interesting. Okay, so I just mentioned there's optimization in computer vision. That's really what I meant to say. There's plenty of problems. I gave a few. I'll come back to them, but I want to step back. So step back means I want to look one version of the history of quantum mechanics. So I'll be very quick, and I'll present one version of the history. And that version goes like this. Um, is the wave idea, the idea that we have waves, of course, quantum mechanics, and it begins with F equal ma is Newton's law, written as the potential energy force. The acceleration is the derivative, and then there was the whole Rococo movement in physics to do Lagrangian formulation, and you have the kinetic energy minus potential, and you create the action. Uh, you create the action out of this, the integral of the Lagrangian over time, and then you optimize the action to the you get the Euler-Lagrange equation. And sure enough, if you apply the Lagrangian of the kinetic energy and the potential energy, you get F equal ma equation. So at that time, many people said, "Oh, who cares? You get the same thing." But it was a nice formulation, and when it was proposed, and to me, to what I want to get is the idea that So that was the main, uh, the lesson I'm taking here. And it's well established. This is, we're talking 1800s. And, uh, and then uh, I move, and again, I'm going a very short story of quantum mechanics. I moved to optics. And in optics, there was then the Fermat principle. The Fermat principle is that light travels the shortest amount of time between A and B. And if it travels the shortest amount of time, then the integral of time to go from A to B, so I'm going from A to B, because of the velocity, there's a medium, so the medium has the refraction index of light divided by refraction index is the velocity in the light velocity in the medium. So I apply dt to this there, and you get this formula for the space. And so you should optimize. The light optimize this integral. It gives you, if you minimize, it gives you Snell's law. And again, it was at the time there was a geometric idea of optics, which light travels the shortest amount of time. So again, an optimization principle for the light as a point traveling, and gave laws like the Snell law satisfy that. Okay. So two optimization principles: one for the light and one for the physics, for the trajectories. In physics, the action, you think of trajectories of particles in physics, and there's an optimal way, which is the Lagrange equation, and so not so unsimilar. The two ideas, happening a little bit in parallel. So then, people start thinking. There was a lot of interest to understand how geometric optics and wave optics. That was an interest then. The wave optics, there was Huygens, there was all these ideas that interference was happening. And there was geometric optics with Fermat principle. And one wonders, what's the connection between them? This is sort of pre-quantum mechanics, And I don't know the times. I think before. And then there was this wave optics. And the wave optics was the following idea. You look, wave optics means how to go from geometric optics, from Fermat principle, to waves. That was the question asked. And one answer was, you, you put as a phase the criteria. And then you sum over all possible trajectories. So now light, which was photons, I don't know, the light was traveling the shortest amount of time, integrate over all possible paths, and that would give you the wave at the end. So it's a sum of all trajectories the light could take. The sum where the optimization criteria is put as a phase. You sum everything as a phase, and you'd get the wave optics. And so I did some, if you're going from A, a mirror, and you explain, and you're going here, you try all trajectories that land on the mirror. It's optimal way is like this as well, and so on. You sum of all of them, and you get the wave equation, which was this one. Parallel to this, there was Maxwell's equation. If you solve the Maxwell equation with removing B on free, you get an equation for the wave, which is the electromagnetic field. And for stationary solutions, you get things that are similar to this. You get equations like this. And sure enough, those equations look similar to those things. That was the connection between wave from the geometric concept to waves from Maxwell's equation. And so there was an understanding that geometric optics and wave optics were kind of being put together. That was understood. And again, understood how? By the sum of all paths of the optimization criteria as a phase. That was in optics. Then came What? Already? Something is not right. Oh, I see, I see. I jumped. No, I will not. I'll do one. I'll come back. I will come back. So, what happened to quantum mechanics? So, Dirac knew about these things, and Dirac said, well, if the phase is the optimization from geometric optics to wave optics, why can't we use the optimization from particle physics, which is the action we just talked a moment ago? Said now the action is the optimization. Let's sum of all actions for all possible paths, and that should give the wave mechanics. And that was Dirac's idea. Feynman learned about it and said, let me calculate. And sure enough, he does the calculations by summing over all paths of the classical action, and you get Schrodinger equation. So you can think the Schrodinger equation, or at least the green function of the Schrodinger equation, as the kernel. So Schrodinger equation was then the reference for Schrodinger equation is a kernel for a given path between time zero and time t. You propagate an initial wave, you get the final wave, and that became the formulation of quantum mechanics. Why this is relevant to what I'm stepping back or to what I want to say is because in this framework, quantum physics is, where's the physics? You know, if you're a physicist, you always want to say the physics is here. It's the only place where there's a physics. It comes from physics, you model, like I heard here a few talks, Coulomb potential, other potentials. And then there's kinetic energy. This is physics. But once you have physics, you get quantum mechanics without any new physics by simply summing things. Just like you get optics by thinking the light travels shortest time. So in some sense, and something I'm going to pick with physicists, and I'm being careful, is that I don't think quantum mechanics has new physics. I think it's just, and just, I don't mean just, it's a statistical framework that's not the one that Boltzmann set up. And what I mean is, I give an optimization criteria, this one, and I mentioned to you before, in other fields, we have other optimization criteria. We are not physicists. We have other things that we want to optimize. And if I want to go from particles, points, data points, to waves, I have a prescription. And the quantum mechanics is, we all know, is not quite Boltzmann statistics, but it's a statistics. At the end, you're going to get, I heard a talk earlier here talking about Born rule, which is the magnitude square of the wave function is density probability. And so you can speak about probabilities in some sense. And, but I get them from any optimization criteria. I don't have to do physics, I think. So that's my starting point. Um, uh, I did the following work. I'm going to mention something practical. I look at this problem of circles in clutter. I look at something that comes now, I step out of physics, and a method that I think is very basic to computer vision and very interesting is half transform, is a voting scheme. you, you, you define every data point detected. For instance, I run a Moller wavelet of a few people here. I detect the response. I vote for every perpendicular line to the response. I vote one, and then I place votes, and I'm voting for the center of the circle. So I detect all the tangents. Of course, there'll be many mistakes. I vote for all the points perpendicular line as a potential center for my circles that I'm looking at. I do the vote, and as I do the vote, I get I get a space of votes, and I look for the magnitude square of those votes or for the magnitude of the votes, and the one who has votes are my centers. And that's a very classical technique of optimization in computer vision, and it's particularly interesting to me meaning for what I'm trying to say, because it's all independent. Every point is independent. They all vote for one space. There's no pairwise. There's nothing long-range interactions in the language of physics. It's all pointwise. Every point you detect, vote for the parameter space. You accumulate votes, and you'll see which places have good votes, which parameters, which are the centers of the circle, if I'm voting for centers, get good votes. And I thought, okay, so with my language, I'm gonna jump from computer vision to wave vision. I'm gonna do my votes, which are one. I'll make my vote still to be magnitude one, but now I'm gonna put a wave there, so that the further away it goes, it has some vibration K, sum of all of that, and it says, oh, I'm gonna sum my votes at every point no longer be one as half transform proposed. You vote one for every point. I will vote with a phase. And now I want to see what do I get out of this. Does this help me? Doesn't help me. So far, I made a connection between quantum mechanics, optimal path, geometric optics, optimal time length. I didn't get too much what do we get out of this, meaning we all know quantum mechanics is very important to explain nature, there's no question, but the question for me, who are at this moment not that interested on the physics per se, but on optimization, what do I get out of this? It's very nice. I'm doing quantum something, I'm doing quantum. Nice, but what do I get out of it? And I want to get to that point now. So I said, oh, I'll vote this way, and let me see what I get. And so I, with the students here, we look at different ways to vote. I can vote based on the magnitude of the wavelet, so how much edge there is where I get, the magnitude of the wavelet, or I just vote one. And on the quantum side, I can vote with the magnitude of the wavelet plus a phase, times a phase, sum of all points, or I can just do the phase. And I'll do some comparisons, and I study this problem here. This is two synthetic examples, as I said before, with more noise. And then we have to be kind of data scientists sometimes, we have to be real. So we lose, this is mouse data, embryos mouse data for reproduction. So this is embryos, and they overlap. And there's a lot of interest in detecting how many, where they are, and so on. This is the result. Well, I have to see. I don't want to make a mistake. Who is who here? Yes. So this is the votes with magnitude, the half transform, and you can see it does so well. This is the votes without the magnitude of the wavelets, not so well. This is the Born rule, which is the wave which I summed it with e to the ikx, and then I take magnitude squared to get probability. Probabilities, which is always the best one. Without the volt, without the real part, I get this thing. So it works, maybe not surprisingly, but it is better than just doing the classical votes. So I have to manage time because I want to get to the question, to some discussion. Okay, so on the path, let me make a technical remark because I open question. I want to say the progress I think I made, but I also want to pose some questions that making me think. So the question, just to say right away, is one question: is when you look at the Feynman path integral and the sum of all paths, and Feynman, the calculations for the Schrödinger equation for the free particle are very easy, standard Gaussian integrals and so on. And you have the double slit experiments, you have diffraction, you see the results. I'm going quick and assuming anyway. So the question that comes is, where is the place for data? In data science, we know we have data. You collect data. We are in a field where data is all data driven, as they say. Data in the story. And I see two places for data in quantum mechanics, and they are very different. One place for data, think of the double where the holes are. You put them close to each other, and there's data because it's real. You have an entrance, you have to make the entrance, and the light has to go through that. So it's a real thing. And so data is real in that sense. Another place to data that is done with quantum mechanics is to say, look, the data is the potential, the V over X is a real value function. It's not complex. And, there are numbers and numbers I could put in. So this may be data. And they're very different. If they are potential, on the e to the I action, potential will come as a complex number. If I put as a double slit, they come as real. So I have a major question in this quantum mechanics formulation for us. I don't have to be too much attached to physics. Is data to be modeled as complex variables, as phases? Should they go to the phase, do an optimization and place them on the optimization term as the I, or should I consider them real? So that's a general, it will appear on everything I'll tell you, it will appear. For example, on the on the on the picture I just show you, it appears. Here, I have those two scenarios. This is all complex. Data is all complex. Here, I have a magnitude of the wave that multiplying, and it's real. It's very different. I want to remind you. One thing is to think I just vote this, magnitude 1, or I can think I multiply by the magnitude of the wavelet response, which is this, which is real. It's a very different way to introduce data. And of course, it makes a difference. And I don't think this is something that in physics, for some reason, it's not it doesn't appear, it's not thought through, is my opinion, in the quantum mechanics. So for example, I'll say, in the Feynman path integral, going back, when you have to do the calculations, the initial condition is critical. The particle has to be localized. Localized means real. I need a real initial value functions. If I just go with complex, everything is complex, the kernel is complex, everything's complex. It's always a constant. The probability to be one everywhere. One can argue if it's all complex, you're not in Hilbert space, it's just plane waves. But regardless of the technicalities, at the end of the day, to do physics, you need initial, what we call localized functions, which means real. Real parts have to be important there. And in data, it's critical to understand these two roles. So that's, I'm saying things that as I do my work, I see the problem appear and how it goes in different ways. Okay, so then I go for shapes. I say, well, if I have a circle, I did mention the circle very early. And this is a circle, is all the points x such that x minus mu square r square 1 minus is 0. So when I think is optimization, I can do the s square, the magnitude of this. That's what I want to optimize. So all the data should make this as small as possible, which means all the data, which is data points, I should find the center and the radius that minimize this quantity. That's how I find all the square. So if this is my optimization criteria to find parameters like center and radius, then as I do the path integral formulation, I sum of all the path with something, different than in case of I don't need to slice, I just compute the action. If I assume the initial, so my criteria of optimization is points at time 0, I can think that I have my points at time 0 minus the center. There's always a constant that you have divided to get the periodicity. Not the periodicity, the oscillations there in physics is the Planck, reduced Planck constant. If I assume my data is, my variable is located on the data without a functions, a bunch of endpoints, I do the convolution, and I get something that's, again, a voting scheme. I have a voting scheme of all the points that vote for the center, and theta represents all the parameters, in this case the radius, sum of all of them. Do the sum. I have a parameter to play, which is the part to be understood. And this gives me a wave, a wave for these points, and this wave can vote for centers, the same way as half transform and complex. So very similar to the idea of half transform, quantum mechanics. The waves come as superposition of things. The concept of superposition is very similar to votes in half space, except by being complex. That makes a difference. But you sum them, and of course you do magnitude square. I have, this is the time that I have. And so in 5 seconds, I'll say I get, because the magnitude square of a sum of waves we have interference, and that's the new phenomena that you have in quantum mechanics that you don't have in non-quantum mechanics. The waves that interfere, positive and negative, you get probabilities to cancel. You get interactions between different points to come out of the magnitude square. So I don't need to model pairwise interactions. They come naturally from the magnitude square. Everybody talks to each other in a precise way. Computationally, it's linear. It's very efficient computation. I get those things. My time finished. Of course, I would love to spend another 3 hours, 10 hours, talk to you. I'll stop here. I have more things to say another day. Thank you very much for the chance. So, uh, follow a bit of a recipe, which is called statistics, but actually quantum mechanics. And the recipe is that the optimization criteria comes as the phase. So there's an optimization criteria, and that's where all the work of wavelets and so on. I know we are connected. We all know that the Morley wavelet is the coherent state, and they are the eigenstate of the oscillator harmonic. Well, there's all the connections, but the optimization criteria is in the phase. So that's one thing to point out, that the phase is the optimization criteria. And the second is that entanglement is a very fashionable thing, very interesting thing. Some people think that the root of entanglement is interference. So below, because entanglement, the way it's formulated by von Neumann, is already, you have mixed states, you're already more complicated. Here we are in that language of information theory, in pure states, and there's only one particle for that matter. In this formulation, I can do more particles, but here's just one particle. And there's a lot of, in physics, the root of all those ideas is interference, more deep than entanglement. The entanglements follow from interference. Is how someone that studies physics, that is a fine way to go back to the roots of physics. So entanglement is sort of following from interference. So in that sense, yes, the fundamental concept is phase interference, with the optimization criteria as the phase. And then there's the real part that I opened the discussion. Thank you. Wow, thanks very much. Thank you.